Imagine crushing Mount Everest into a sugar cube. Now imagine crushing our entire planet, all 6 sextillion tons of it, into something the size of Manhattan. What you're imagining shouldn't exist. The laws of physics as we understand them say it can't exist. Yet across our galaxy, there are hundreds of millions of these impossible objects, spinning silently in the darkness, defying every intuition we have about matter, gravity, and the nature of reality itself. They are neutron stars, and they are the most extreme objects in the universe that aren't black holes. In 1967, a graduate student named Jocelyn Bell Burnell detected a signal that shouldn't have been possible, a radio pulse so precise, so regular, that her colleagues briefly wondered if they'd discovered alien intelligence. What she'd actually found was something stranger than fiction, a dead star spinning hundreds of times per second, compressed to densities that make diamond look like empty space. Today, we journey through evidence that challenges everything we thought we knew about the limits of matter itself. November 28, 1967, Cambridge, England. Jocelyn Bell Burnell was reviewing data from a new radio telescope when she noticed something peculiar, a scruff in the recordings that appeared at the same point in the sky night after night. The signal pulsed with metronomic precision, once every 1.3373 seconds, never varying by more than a millionth of a second. Nothing natural should behave this way. The team considered every possibility: equipment malfunction, terrestrial interference, and yes, for a brief period, they entertained the possibility that they'd detected an alien beacon. They even labeled it LGM-1, Little Green Men 1. But when Bell Burnell discovered a second signal, then a third, all from different parts of the sky, the alien hypothesis collapsed. The universe, it seemed, was full of these cosmic lighthouses. What could produce such impossible precision? The answer came from theoretical work that had been languishing in obscurity for 3 decades. In 1934, astronomers Walter Baade and Fritz Zwicky had proposed something outrageous. When massive stars explode as supernovae, their cores don't disappear. They collapse into objects so dense that protons and electrons merge into neutrons, neutron stars. At the time, the idea seemed absurd, but Bell Burnell's discovery proved these objects weren't just theoretical curiosities, they were real. To understand what a neutron star actually is, we need to grasp the sheer extremity of what happens during stellar collapse. When a star, at least 8 times the mass of our Sun, exhausts its nuclear fuel, gravity wins. The core implodes in less than a second. In that moment, matter gets crushed with such violence that atoms themselves are destroyed. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos. What remains is a sphere of neutrons, packed together as tightly as physics allows. The numbers are staggering. A neutron star typically measures just 20 kilometers across, about the size of a city. Yet it contains 1.4 to 2 times the mass of our entire Sun. A single teaspoon of neutron star material would weigh approximately 10 million tons. If you could somehow bring that teaspoon to Earth, it would punch through the planet like a bullet through tissue paper. The density is almost incomprehensible, around 500 million tons per cubic centimeter. This is the same density as an atomic nucleus. Imagine taking all of humanity, 8 billion people, and crushing us down until we fit into a space the size of a sugar cube. That's the density we're talking about. But density is just the beginning. Here's where neutron stars become truly bizarre. When that massive stellar core collapses, something remarkable happens. As it shrinks, it spins faster. The same principle that makes figure skaters spin faster when they pull their arms in. But while a figure skater might increase their rotation from 1 revolution per second to 5, a neutron star goes from 1 rotation every few weeks to hundreds of rotations per second. The fastest known neutron star, designated PSR J1748-2446 AD, spins 716 times every second. At its equator, the surface is moving at approximately 24% of the speed of light. This is a ball of matter denser than an atomic nucleus, with a gravitational field 200 billion times stronger than Earth's, spinning so fast that it completes 750 million rotations every million years. And it does this without flying apart. Think about that. At those speeds, the centrifugal force should rip the star to shreds. The equatorial regions are trying to fly off into space at a significant fraction of light speed, yet something holds it together. But the evidence forces us to confront an uncomfortable possibility. We don't actually understand what's inside these objects. We don't know what matter becomes under these conditions. And recent observations suggest that neutron stars might be doing something that shouldn't be physically possible. For decades, astronomers measured neutron star masses and found something puzzling. They all seemed to cluster around 1.4 times the mass of the Sun. This made sense. Theory predicted that neutron stars above a certain mass, about 2.3 solar masses, should collapse into black holes. But then came the outliers. In 2010, astronomers studying PSR J1614-2230 made a shocking discovery. Using precise measurements of how the neutron star's gravity affects its companion star, they calculated its mass, 1.97 solar masses, the heaviest neutron star ever measured. This finding pushed against theoretical limits. The equations describing neutron star matter, the equation of state, suggested that objects this massive shouldn't be stable. Then in 2013, the record broke again. PSR J0348 plus 0432, 2.01 solar masses. And in 2019, the most remarkable measurement yet, a neutron star in the system PSR J0740 plus 6620 clocked in at 2.14 solar masses, possibly even higher, with uncertainties pushing toward 2.3 solar masses. These objects exist at the absolute edge of stability, the boundary between neutron star and black hole. Something is supporting them against gravitational collapse, but we don't know what. Neutron stars are born hot, surface temperatures exceeding 1 million degrees. Over millions of years, they should cool predictably, radiating their heat into space. But they don't cool the way they should. NASA's Chandra X-ray Observatory detected several neutron stars that cooled far faster than theory predicted. The most dramatic case, the neutron star in the supernova remnant Cassiopeia A, cooled by 4% in just 10 years. That might not sound like much, but it's equivalent to the star losing approximately 150 degrees in a decade. For an object that should maintain its temperature for millennia, this is bizarre. The rapid cooling suggests something unexpected happening inside. One possibility, the core has reached such extreme densities that neutrons are pairing up into a superfluid, a frictionless fluid that flows without viscosity. When this phase transition occurs, it releases enormous amounts of heat very quickly, like water releasing energy when it freezes. But if the cores are superfluids, that means something remarkable. These dead stars contain the largest frictionless oceans in the universe. Oceans not of water, but of quantum matter exhibiting collective behavior across stellar scales.
On December 27, 2004, every satellite monitoring gamma-ray emissions in our solar system was suddenly blinded. A wave of energy hit Earth from a neutron star 50,000 light-years away. In 1/10 of a second, this distant object, designated SGR 1806-20, released more energy than our Sun emits in 150,000 years. If the burst had occurred within 10 light-years of Earth, it would have caused a mass extinction. What happened? The neutron star's crust, a crystalline solid about a kilometer thick, suddenly cracked. This wasn't a small crack. The entire crust shifted by less than a millimeter, but that tiny adjustment in an object with such extreme gravity released apocalyptic amounts of energy. Scientists call these events Starquakes, and they reveal something remarkable about neutron star structure. These objects have crusts, solid surfaces made of atomic nuclei packed into crystalline lattices. This crust is the strongest material in the universe, 10 billion times stronger than steel. Yet the immense magnetic fields and gravitational stress can suddenly shatter it. But this represents just one piece of a much larger puzzle, because beneath that crust lies something far stranger. Imagine journeying to the center of a neutron star. This is a trip into conditions that don't exist anywhere else in the universe outside of black holes. The outer crust, that kilometer-thick shell of crystalline nuclei, is the last place where matter resembles anything we recognize. Temperature? Around 100,000 degrees. Density? 1,000,000 times that of Earth's center. Descend deeper. You pass through the inner crust, where the nuclei become so neutron-rich they start dripping neutrons into the spaces between them. It's called neutron drip, and it's the first sign that you're leaving normal matter behind. Keep going. You reach the outer core. Here, neutrons flow freely in a dense liquid with a smattering of protons and electrons. Density? 100 million tons per cubic centimeter. The neutrons are so tightly packed they exhibit quantum behavior collectively, billions upon billions of particles acting as a single quantum system. But at the very center, the inner core, physics breaks down completely. We don't know what happens there. Computer simulations can't reliably predict the behavior of matter at such densities. Several possibilities exist, each stranger than the last. Hyperons might form, neutrons transformed into exotic particles containing strange quarks. Or the neutrons might dissolve entirely, their constituent quarks floating freely in a sea of deconfined quark matter. Some physicists suggest even stranger possibilities: kaon condensates, pion superfluids, or configurations of matter that don't exist in our standard model of particle physics. The most remarkable discovery involves recent research from LIGO, the gravitational wave detector. August 17, 2017. LIGO detected gravitational waves from two neutron stars spiraling into each other, 130 million light-years away. This wasn't just another gravitational wave detection. For the first time, telescopes saw the light from the same event, a kilonova, the explosive merger of two neutron stars. The data was extraordinary. In the final moments before collision, these two neutron stars were orbiting each other hundreds of times per second, moving at a significant fraction of light speed. The gravitational waves allowed scientists to measure how each star deformed under the other's gravity, a property called tidal deformability. Here's what that revealed. Neutron stars are stiffer than many theories predicted. They don't compress easily. This means the equation of state, the relationship between pressure and density, must be harder than some models suggested. But the implications go deeper. When the neutron stars merged, they created something massive, perhaps 2.7 solar masses of neutron star matter. For a brief moment, maybe a second, maybe less, this hypermassive object existed before collapsing into a black hole. In that instant, matter reached densities higher than anything else in the visible universe. The gravitational waves from that moment carried information, and that information suggests something unsettling. At extreme densities, matter might undergo a phase transition, transforming from neutrons into something fundamentally different. If neutron stars represent the extreme, magnetars represent the extreme of the extreme. These objects possess magnetic fields trillions of times stronger than Earth's, the most powerful magnetic fields in the universe. A magnetar's magnetic field is so intense that it warps the very atoms of its crust, stretching them into needle-like shapes aligned with the field lines. The numbers are difficult to fathom. A typical magnetar's magnetic field strength reaches 100 billion to 100 trillion times Earth's magnetic field. If you were within 1,000 kilometers of a magnetar, the magnetic field would be fatal, not from radiation, but because the field would be strong enough to disrupt the electromagnetic bonds holding your atoms together. These fields store tremendous energy. When a magnetar's crust cracks during one of those starquakes, the magnetic field lines can snap and reconnect, releasing energy equivalent to thousands of supernovae. These outbursts produce the most powerful explosions in the universe, apart from the Big Bang itself. But here's what's truly strange. We don't know how magnetars get such powerful fields. Current theory suggests they're born with them, formed in the most violent supernovae, where rapid rotation and convection create a dynamo effect. Yet recent observations reveal magnetars with relatively slow rotation, contradicting this model. The evidence extends beyond unusual magnetic fields into the realm of quantum phenomena at cosmic scales. At the heart of the neutron star mystery lies a deceptively simple question. What is the relationship between pressure and density inside these objects? This relationship, the equation of state, determines everything about a neutron star. It determines the maximum mass before collapse into a black hole. It determines the radius for a given mass. It determines how the star responds to gravitational waves, how fast it cools, even how it rings when disturbed like a bell. But we don't know the equation of state, not precisely. The problem is fundamental. To calculate how matter behaves at neutron star densities, we need to solve the equations of quantum chromodynamics, the theory governing how quarks and gluons interact. But these equations are so complex that even the world's most powerful supercomputers can't solve them reliably at the densities found in neutron star cores. Physicists have proposed dozens of different equations of state, each making different predictions about what's inside these stars. Some models predict pure neutron matter all the way to the center. Others predict exotic hadrons, deconfined quark matter, or even stranger possibilities. Recent observations have narrowed the options, but significant uncertainty remains. Research teams at institutions like MIT, the Max Planck Institute for Gravitational Physics, and RIKEN in Japan are attacking the problem from multiple angles. They're using gravitational wave data, X-ray observations from NASA's NICER mission on the International Space Station, and advanced nuclear physics experiments to constrain the possibilities. The goal? Measure the radius and mass of neutron stars with such precision that only one equation of state fits the data. This forces us to reconsider fundamental assumptions about the relationship between quantum mechanics and gravity. Quantum mechanics usually describes tiny things, atoms, photons, subatomic particles. Gravity describes large things, planets, stars, galaxies. These two realms rarely intersect, but neutron stars are quantum objects at human scales, actually at city scales. Inside a neutron star, quantum effects dominate despite the object being 20 kilometers across. The neutrons in the core form a superfluid, exhibiting quantum behavior collectively. The protons form a superconductor, allowing electrical current to flow without resistance. These aren't small quantum systems, they're the largest quantum fluids in the universe. This has profound implications. Dr. Nicolas Chamel at the Free University of Brussels studies neutron star crusts and describes them as cosmic laboratories for quantum many-body physics. The inner regions contain nuclear pasta, matter arranged in bizarre configurations like rods, plates, and tubes, shapes that emerge from the competition between nuclear forces and Coulomb repulsion. This nuclear pasta exists in a narrow zone near the base of the crust, and it may be the strongest material in the universe, even tougher than the crystalline crust above it. Breaking nuclear pasta requires forces that dwarf anything terrestrial technology could produce. But the quantum effects go even deeper. Research from Nikolai Gerlebek at the University of Bremen suggests that neutron stars might exhibit frame-dragging effects so extreme that space-time itself becomes twisted into a vortex around the star. This isn't just gravitational lensing, it's space-time literally being stirred like honey, carrying nearby objects in its rotation. Recent work on so-called exotic compact objects suggests neutron stars might blur the line between normal matter and something else entirely.
In 2017, NASA installed an instrument called NICER on the International Space Station. Its mission? Map the surface of neutron stars with unprecedented precision. The technique is elegant. As a neutron star rotates, hot spots on its surface move in and out of view, creating pulses of X-rays. By analyzing these pulses in exquisite detail, NICER can reconstruct the shape of the star and measure its radius to within kilometers. Recent breakthroughs suggest we're on the verge of solving the equation of state problem. In 2019, NICER measured PSR 0003 plus 0451, finding a radius of about 13 kilometers for a 1.4 solar mass star. This measurement favored stiffer equations of state, those predicting that neutron star matter resists compression more than previously thought. But there was something else in the data. The hotspots weren't where anyone expected. Instead of being near the magnetic poles, they appeared at unexpected locations, suggesting that the magnetic field geometry is far more complex than simple dipole models predict. Then came measurements of PSR 0740 plus 6620, that 2.14 solar mass behemoth. NICER found its radius to be approximately 13.7 kilometers. This is crucial. If the radius had been significantly smaller, it would have implied that the matter becomes very soft at high densities, possibly indicating a transition to quark matter. But the measurement suggests the matter remains relatively stiff even at extreme densities. The implications are staggering. These measurements, combined with gravitational wave data from neutron star mergers, are finally pinning down what matter becomes under the most extreme conditions in the universe.
But what if some objects we've classified as neutron stars aren't neutron stars at all? There's a theoretical possibility that chills physicists: strange stars. Strange stars would be made not of neutrons, but of quark matter, a soup of up, down, and strange quarks roaming freely. They would be the same size as neutron stars, the same mass, emit similar radiation, but fundamentally, they'd be different objects. The strange quark matter hypothesis suggests that this state might actually be the true ground state of matter, more stable than normal atomic matter. If true, all matter is metastable, waiting for the right trigger to transform into strange quark matter. This is not science fiction. Research teams at facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory are creating quark-gluon plasma, briefly recreating the conditions of the early universe to understand phase transitions in dense matter. Some neutron stars might contain hybrid cores, neutron matter in the outer regions surrounding a quark matter core. Others might have transitioned completely, becoming strange stars masquerading as neutron stars. How would we tell the difference? There are subtle signatures. Strange stars should be slightly more compact than neutron stars of the same mass. Their cooling rates might differ. Their oscillation modes, the way they vibrate when disturbed, would produce different gravitational wave patterns. Future gravitational wave detectors might catch a neutron-star merger that reveals these differences definitively.
We're entering a golden age of neutron star science. The next generation of gravitational wave detectors, Einstein Telescope in Europe and Cosmic Explorer in the United States, will be operational in the 2030s. These instruments will be so sensitive they could detect neutron star mergers across the entire observable universe. Every merger will provide data on the equation of state. The Square Kilometer Array, a radio telescope currently under construction, will discover thousands of new pulsars. Some will be in exotic binary systems where their masses can be measured with extraordinary precision. China's Hard X-ray Modulation Telescope and the upcoming Enhanced X-ray Timing and Polarimetry mission will map neutron star surfaces with unprecedented resolution. But perhaps most exciting are the theoretical advances. Recent breakthroughs in lattice quantum chromodynamics, simulating quark interactions on supercomputers, are approaching the densities found in neutron star cores. Within a decade, we might finally calculate from first principles what happens inside these objects. The convergence of observation and theory is accelerating.
The most profound implications emerge when we consider what neutron stars might reveal about physics beyond the Standard Model. The Standard Model of particle physics is remarkably successful. It describes the behavior of all known particles and 3 of the 4 fundamental forces with exquisite precision. But physicists know it's incomplete. Neutron stars might hold the key to new physics. At densities several times that of atomic nuclei, densities that definitely exist in neutron star cores, theoretical calculations become unreliable. We're extrapolating beyond tested physics. New particles might appear, new forces might emerge, the fabric of space-time itself might behave differently. Consider dark matter. This mysterious substance makes up 85% of the matter in the universe, yet we've never directly detected it. Some theories propose that dark matter consists of exotic particles that barely interact with normal matter, except at extreme densities. What if neutron stars accumulate dark matter? Over millions of years, a neutron star passing through dark matter-rich regions would capture these particles. They'd sink to the center, where densities and temperatures might allow them to interact or decay in ways impossible in normal matter. This could affect cooling rates, trigger additional starquakes, or even eventually destabilize the star. The NICER team is actively searching for these signatures. But there's an even more radical possibility.
Some theoretical physicists, including researchers at the Perimeter Institute for Theoretical Physics, have proposed something extraordinary. Neutron stars might contain mirror matter. Mirror matter is a hypothetical form of matter predicted by certain extensions to the Standard Model. It consists of particles identical to normal matter, but interacting through mirror versions of our forces. A mirror electron, mirror proton, mirror photon, an entire parallel particle physics operating alongside our own. Here's the crucial detail. Mirror matter would only interact with normal matter through gravity and possibly weak nuclear force. If mirror matter exists, the extreme densities in neutron star cores might force it to interact with normal matter in observable ways. Some researchers suggest that the rapid cooling observed in certain neutron stars could be explained by mirror matter forming in the core and carrying away energy. Others go further. They propose that some neutron stars might be hybrid objects, normal matter shells surrounding mirror matter cores. These would appear almost identical to pure neutron stars, but would have subtly different masses, radii, and oscillation frequencies. The evidence isn't conclusive, but it's intriguing enough that serious research programs are investigating these possibilities.
At the deepest level, neutron stars force us to confront the ultimate question. What is the maximum density that matter can achieve before it stops being matter? There must be a limit. Above approximately 2.3 solar masses, the exact value depends on the equation of state, gravity becomes so strong that nothing can resist collapse. The object becomes a black hole, and all information about its internal structure vanishes behind the event horizon. But approach that limit from below, and strange things happen. At densities 5 to 10 times that of atomic nuclei, matter might undergo a phase transition to quark matter. This wouldn't be a gradual change, but a sudden transformation, like water turning to ice. Some models predict that this transition is a first-order phase transition, discontinuous, with both phases coexisting briefly. If this is true, then there could be hybrid stars with sharp boundaries between neutron matter and quark matter inside them. Others suggest the transition is a smooth crossover with no distinct boundary. The difference matters enormously. A first-order phase transition would soften the equation of state, lowering the maximum mass of neutron stars. A crossover would allow higher masses. The existence or non-existence of neutron stars above 2.5 solar masses would tell us which scenario is correct. Recent observations from the LIBO-Virgo collaboration hint at objects in the mass gap between the heaviest neutron stars and the lightest black holes. One such object, discovered in gravitational waves, has a mass around 2.6 solar masses. Is it a heavy neutron star, a light black hole, or something else entirely? A hybrid star, perhaps, or a strange star? We don't know yet, but the answer will tell us something profound about the nature of matter at its absolute limit.
We began with an impossibility. Objects that compress mountains into sugar cubes, that spin hundreds of times per second without flying apart, that possess magnetic fields powerful enough to disintegrate atoms. Now, we see them differently. Neutron stars are laboratories where the universe performs experiments we can never replicate on Earth. They reach densities where quantum mechanics meets gravity in ways that challenge our deepest theories. They exist at the edge of the possible, the boundary between matter and black holes, between understood physics and mystery. What have we learned? We've learned that matter is far stranger than anyone imagined, that quantum effects can dominate objects 20 kilometers across, that the universe contains superfluids the size of cities, magnets that could destroy worlds, and phase transitions that might reveal physics beyond our current understanding. But vast unknowns remain. We don't know the equation of state. We don't know if quark matter cores exist. We don't know if some neutron stars harbor mirror matter or accumulated dark matter. We don't know where the transition to black holes truly occurs. What we do know is this: every observation brings us closer. Gravitational wave astronomy, advanced X-ray telescopes, new nuclear physics experiments, they're converging on the answer. Within the next decade, we will likely solve the mystery of what's inside neutron stars. We will know the equation of state. We will understand the phase transitions. We will finally grasp what matter becomes when pushed to its absolute limit. And in understanding these extreme objects, we'll understand something fundamental about the universe itself, about the relationship between quantum mechanics and gravity, about the nature of matter, about the limits of physical law. The universe is vast. The mysteries are endless. But neutron stars, those impossible objects spinning in the darkness, are teaching us that reality is far more remarkable than we ever dared imagine. The journey continues.